Good. Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. It's my great pleasure to introduce today's speaker, Professor Xiaofeng Wang. Professor Wang is an associate professor at Indiana University at Bloomington. He received his PhD in computer science from the CMU in 2004. And he has published many papers in top security conferences. And the work he talked about today, I believe, are results from two of these papers. And here's Xiaofeng.
Okay, I'm very happy to be here to give the talk. I'm just like Yinghui mentioned, I'm associate professor at School of Informatics and Computing, Indiana University. At IU, we have a security team with six faculty members. We are working on just a wide spectrum of security area, including cryptography and applied cryptography, system network security, and security and policy, security and economy, and a very large spectrum of research area. I myself leading a research group with six faculty members. Working on two major directions. One important direction working on is security privacy in bio and health informatics. And the second thing we are working on is security privacy in the cloud computing. Actually, this is my second time to be here to give the talk. The first time, I present our research on how to use program specialization to facilitate and secure computation outsourcing. And when the computation related to human genome data. And the research today I'm going to talk about our research on another category, on cloud computing. And I'm going to present you guys our discovery of some, very, important, and a very serious information leak in software as a service. Computing paradigm. And software service is the backbone of cloud computing. This is a joint work with Microsoft Research and a bunch of my highly talented students. So what we are talking about here is a web application. Right, and the web application becoming a kind of replacement for desktop application. Why? Because people tired of having to spend a lot of money to buy the desktop application that end up being used only occasionally. And once you bought a piece of code, you have to maintain it. And whenever there's a new version, you have to upgrade it. And whenever there is a loophole, you have to patch it. And oftentimes you have to reboot your computer, and it's just terrible. So people think about why can't we using a new way to deploy the software. For example, and we can have a bunch of web servers which host a lot of applications. So if you want to use one of them, the only thing you need is just a browser. You just go to the website, click a button, so you can use one of them, right? So what happening there is the application automatically shift the client-side particular user interface to your browser. So you interact with user interface and command the whole application to accomplish your task. So this sounds a very nice way to do the computation. But this new computation actually comes with new security and privacy implication. The major problem is here. Originally you have the whole piece of code, running on your desktop, right? So at the very least, the information flow, all the data information flow within the application is safe. But now you break it up into two pieces. One part running in the browser, the other part running on the server. So the internal information flow of the program actually exposed to the network, right? And when this happens, how can we protect it? And the simplest way is encrypted, right? But encryption working on individual packets. It does not care about the state of application and does not care about the semantic of the application. Well, and the communication between the client side and server side of application is very complicated. It is the communication that used to keep both components stay synchronized. right? So it carries a lot of information. So the gap between these two ends could be explored by adversary to figure out sensitive user data. So that's the observation that motivated our research, and led to our, I think, quite interesting discovery. So just as I mentioned, once you encrypt the data, adversary can no longer see the content of the packet. But they still can observe something just like number of packets, inter-packet timing, and the size of the packets. And such information, which called side channel information, has been studied for decades. And people discovered a lot of information leak by simply looking at those side channel information. And here's the recent one. If you look at encrypted VoIP packets, there's a chance I can figure out the word both party communication party are speaking. If you are looking at encrypted video streaming, you might be able to figure out the title of the movie. But and if you're a big fan of an animated channel, just like Tool, and you could get upset because adversary who monitor your communication, looking at the packet size and sequence, they could be able to figure out which website you are visiting, what kind of content you are downloading. So all these are very, very serious threat, just having studied by previous work. But our research show, and with this software as a service era, the threat of side channel information leak has been elevated to a new level. And it's understandable. Why? Because, now what we are dealing with is no longer those stateless communication, right? What we are dealing with is the whole application, a very complicated application, which is doing all kinds of work. So the interaction between applications client-server component is very complicated. So there's a chance adversary could figure out highly sensitive data. This unfortunately has been confirmed by our research. So this is what we discovered, and it's a very shocking result. And we found, a surprisingly detailed user information can be leaked out. Actually, it's being leaked out from several high-profile, top-of-line web applications. So the type of information we can find include personal health information. For example, if you are using some an online health information system, and I look at your traffic patterns, I can figure out and your disease, your therapy, your medicine, your doctor, whatever information. And if you are using online, and text software, right? Although the communication has been encrypted by HTTPS, I can still figure out your adjusted gross income, your family income. I can pin it down to a very small range. If you are doing investment online, right, what I can do is I look at encrypted traffic. I can figure out which mutual fund you are investing, and your investment strategy. How did you allocate your fund? And another interesting thing is, and in the corporation environment or in the in any organization, for example, just at Purdue, and we have a Wi-Fi communication, but the Wi-Fi communication has been protected, has been encrypted, right? So the communication between your laptop and the Wi-Fi hotspot has been encrypted using the technique just like WPA, WPA2. So, but even if all the communication has been encrypted, an adversary without any credential, the only thing this guy has is just a Wi-Fi, just a sniffer. It can pick up all this encrypted traffic and figure out and analyze it to figure out the query words you enter to the big search engine, just like Google, Yahoo, and Bing. So the problem becomes so serious, and we contact all these affected organizations. Some of them actually require us to keep silent, to keep their, at the very least, the name of their product anonymized. And which we did in our publication, and I'm not going to show you the name of those applications just in the talk. But let me tell you, and they are very, very popular applications. I guess many of you guys are using them. So be careful. And more seriously, the root cause of this problem are some fundamental feature of web application. That is, and the communication is stateful. Just as I mentioned, it's application. It's internal information flow of application. Application is stateful, right? So looking at the traffic, actually it reflects the stateful interaction between applications, application different component. So it carries a lot of information. Low entropy input. Today increasingly just those web applications use this kind of just Ajax driven just widget. Just want to make life easy. Today you click a button, right, and you move your mouse. Just those small activity actually trigger network interaction, and your user interface will change. And these things can be observed by adversary to figure out your input. And a significant traffic distinction, and you choose this button or that button, will download different web page. And each web page will have different JavaScript code, will have different picture, will have different video clip, right? And the traffic distinction will become just so large, it becomes extremely difficult to hide. And the defense is highly non-trivial. Of course, the simplest way you always is conceivable. We can pad packets, we can add a noise, right? But our research shows if we want to do it blindly, in application agnostic way, that is, I don't want to care about where the problem is. I just want to add a noise, pad packets without caring, just a specific feature of application. Our research shows if you are doing something like this, in many cases you may end up with just introduce a huge amount of communication overhead, and without completely eliminating this kind of problem. So it's a very serious problem. So our research, once we published, actually receive just intensive media coverage. So here's some example, and a lot of medias actually report our research. Someone even wikid our work. So now you go to just Wikipedia and search side channel leak, and just inside this category you can find a citation to our work. And just there are a lot of you can simply go to Google and use this keyword side channel leak in web application. You can find a lot of citation. Okay, so before I come to detail of work, I'd like to show you a video demo. Sorry. So this is what we did, and consider you have a laptop, which is just in a corporation environment, and its communication with the Wi-Fi hotspot has been protected by WPA2, right? It's completely secure, right? And then you use this laptop to enter some keywords. For example, in this case, you enter the keywords, query words sniff, right? Then let's go, go to the reception area. And then we discover another computer, another laptop. That computer, does not belong to the organization without any credential, right? The only thing it has is a Wi-Fi sniffer. It picks up all these encrypted packets and do analysis. Let's see what we can find. We can pretty accurately figure out, the query words you enter to the search engine, and we can find out, the letters enter to the search engine. The question is, how could this happen? It's impossible. Just looks like, and just because every packet has been encrypted, including query words. How could this happen? The reason we can figure it out is just because just today's web application extensively use this kind of Ajax widgets, which called suggestion list. And so the game just like this. Whenever you key in the first letter, right? And Google just use this letter to retrieve a suggestion list. And just a different letter, in many cases, will give you a different list. And the different list actually with distinctive packet size. And so although you encrypted, you can hide the packet size. So looking at the packet size, we can figure it out. And in some cases, although the first letter we cannot, and the first two letters will give us the suggestion list with the same size. But we don't need to worry about it. Why? Because just when you enter the second letter, Google use these two letters and retrieve another list, and with a distinctive size. right? So even if we can't tell apart from the first letter, but looking at the second letter, we can figure it out. So essentially, just this process has formed a finite state machine. The state transition has been characterized by the packet distinctive packet size and the sequence. So afterwards, we can build up this model offline. Then you're doing when you are doing online search, right? And they can just pick up your encrypted packets and put it as input to your model, to finite state machine, to find out which letter you entered, which words you entered. And this is what we did, and this looks like completely feasible. And you may say, Google, Bing, Yahoo search, all these query words are public, they're no secret. But imagine, it's no secret to us. But think about, someone sitting outside Microsoft's, main building and monitor what that development team does, right? And in this case, and the searching words you can figure out more or less reflect what they are doing. This could carry a lot of sensitive information. And a similar technique, actually, the problem becomes even more serious. After we published a paper, actually, we found Yahoo took some action to mitigate this threat, and they can allow you to turn off this suggestion list. And the functionality they provide is when you key in the first letter, there's no suggestion list. When you key in the second letter, I don't remember second or third letter which triggered the suggestion list. But the interesting thing is Google actually they provide a new functionality called Google Instant. So this time, not only the suggestion list changes, but the whole page changes. And it changes with every letter you enter. So just give a huge amount of information. Okay. Before I come to the second attack, again, I'm going to show you a video example. This time, we are attacking, a famous, a very, very famous, and online health information system. Again, because we are not going to, because we promise we are not going to put their name up front, right? So we mask some information. So you can see what's happening here. Okay. Can't I just make it full screen? Yeah. So you enter your user ID, password, you get into this system, right? Then then you have to add your profile. Then add your profile. The first things you can you need to select your just a medical condition, your disease. Unfortunately, they use this kind of suggestion list, which we can figure it out. And then you can use this list to choose the medicine you are taking. In the third step, you choose your specialist. Enter where you are. Then you send a request to the server. So there's another machine, just a sniffer, which of course has no credential to access your data, does not know the secret key. But they just do all this analysis. So this is what they can find. What we can find. I know everything. Your disease condition, your medicine, and your specialist. Everything. Encryption, no encryption does not matter to us. And this is just actually just again the question becomes how could this happen? I think you already know part of the answer. Because of a suggestion list. Because of a suggestion list, right? And they use the suggestion list, and so at the very least we can figure out your disease. But for the medicine, I choose it from using this kind of just mouse selection. So the idea is you first enter the initial letter of the medicine, right? Then from the server I retrieve a list. Then from the list you can select the specific medicine you are taking. You click it, it's sent to the server. But just as the idea is very similar. Your different initial letter give you different list, right? And a different list have distinctive packet size. And when you choose an item on a list, right? It also generates some special packets with distinctive packet size, other traffic features. We can use to fingerprint the whole communication. Then use this approach, we can pretty accurately figure out, just which website and just what kind of information you enter to the system. This could happen just because this no entropy input. If you simply type as you can imagine, if you simply type your disease condition without any help into the system, and just look at the packet size and sequence, it's going to be very difficult to figure it out. But now what's happening there is, just you type a single letter, then Google give you the whole list. And this whole thing can be predicted, right? And it can be fingerprinted using your packet feature. So what you entered is a small amount of information with no entropy. Then looking at this feature, we can reverse engineer, figure out what kind of things you entered. And the third part is a little bit tricky. And you find a doctor, and then you have to just after you select doctor, you have to provide a special piece of information, and that is where you live, so that they can find a specialist and close to your geographic location. And this piece of information could be difficult to figure out because you have to manually enter your zip code and your state, whatever, all this information. But we found, just in many cases, we just look at your IP address. The binding between the IP address and your geolocation is not unique. But at very least, it can give you some clue. For example, you're from Indiana, or you're from this particular region, so we can check multiple places unless we fingerprint this particular person. And another interesting property here is, and we can take advantage of the stateful information. The application state. And the state is useful because it binds different pieces of information together. Just think about, and your disease and your medicine and your doctor, these three pieces of information are not independent from each other. Is that right? And you have infected by certain kind of disease, so you need a special type of antibiotic. So you need a special type of specialist. Is that right? So they are correlated. So one thing we can do here is, even if we kind of uniquely identify your disease, your medicine, and your doctor, but we can reduce the anonymity set, then we can do intersection attack. We intersect them. Right? And the result in many cases can give us unique answer. And again, and we also studied two very famous online text preparing software. And again, we use anonymized name. I'm not going to tell you what they are, but the only thing I can say is they are very famous. A lot of people are using them, and they are very much care about their reputation. So that's the reason we have to anonymize everything. And so I think this is not the problem of these two type of software. Is the whole idea of it's a pervasive problem for this type of application. Just for those online text software, what they are doing is, and they first give you a set of questions. You answer this question, then according to your answer, they give you another set of questions, so on and so forth, until you finish answer all the questions. They come up your text report, right? But as you can imagine, just this kind of back forth actually expose the control flow of the program, because your answer actually just allow the program to make a decision what kind of question set they need to pick up, so on and so forth, right? So Adversary monitor and your traffic feature could fingerprint different execution paths, and then from those execution paths to figure out your data. Here's a more concrete example. Just think about one, specific credit, just deduction about child credit, and just a lot of people here is very young. You may not be familiar with U.S. tax law, but just for those who does, just I think just and you can get some money once you have some kids, right? and just if your income is below 110K, you can get all this just a child credit. If your income is go above 110K, so what's going to happen is, for every additional just $1,000 income, and just you are going to lose 50, just $50, just tax credit. And so the interesting things is, so just we're looking at this data transition, right? And from the decision point and from the branching condition, we can go through these three paths. Not eligible, you can get full credit, or you only can get partial credit. These three branch conditions. But each branch condition has a distinctive traffic feature. You are going to download the form with different size. So these things can be fingerprinted by adversary. So monitor your encrypted communication. They can easily figure out whether you are just which path you are going down. In other words, they know whether you are adjusted gross income, your family income is above 150K. Just when this happens, you will not be able to claim any child credit, or below 110K, right? At least they can, or your income is belong to something in between. And another interesting observation we found is, and in some cases, we don't even need to just fingerprint the individual path, execution path to figure out sensitive information, because in just those text, just preparing applications, they just full of this kind of asymmetric execution paths. Just here's another example. If you want to apply for student loan interest credit, maybe some of you guys will do, and then they will ask you a bunch of questions again. If you are not entitled for this kind of credit, then just the system will no longer ask you any question. They just return and move on, right? But if you are eligible, then they are going to just send you another set of questions to ask you your paid interest. So in other words, if you are not eligible, there will be only one round of communication. If you are eligible, there will be 2 rounds of communication. So in other words, they only need to count the number of rounds communication they observe. They can figure out if your income is above 145K. When this happens, you are no longer eligible, or below 115K, and in this case, you can get full credit. So this is what we did. We studied only 9 different, credit deduction, and we already can come up with this chart, and if you go through all this, 9 different credit deduction, then looking at your traffic pattern, we can pin your family income down into one of these interval. But remember, this is nothing but a tip of the iceberg, and there are totally 350 different credit and deduction. If we just study all of them, I'm pretty sure I can narrow your possible income to a very, very small range pretty accurately. Our last attack is on a very famous online, investment software. It's so famous, I myself is using that, and and what we can discover is the way you are doing investment, what kind of mutual fund you invest, and your investment strategy. How did you allocate your fund? And this could happen is because the companies, they use this kind of nice graphic representation of the performance of different mutual fund. So whenever you go to your portfolio, right, they just represent to you the performance of the fund you're investing, use a curve, right? And this figure actually turned out to be downloaded from another source, from just Market Watch. Is a public source. Everyone can access the performance of the individual funds, and no secret. Everyone knows that, right? Then what we can do here, although it's also encrypted by HTTPS, but the packet size tells a lot, and they have distinctive packet size, and so we can use the packet size to fingerprint individual funds. So just looking at what the size of packets go from that company's website to your browser, we can pretty accurately figure out what kind of the type of the name of the mutual fund you are investing. And the second thing is a little bit tricky. We want to understand the way you allocate your fund, right, and your investment strategy, but in this case, we encounter some problem because and although they also provide you this kind of pie chart which describe how did you allocate your fund, right? But the resolution of the pie chart is rather small, and as you can imagine, the possible way of allocate the fund is huge, right? The number of possible ways to allocate this fund is huge. So in many cases, we end up with a specific packet size. We may have hundreds of possible allocation, which can be mapped to that size. So it looks like we have a sufficiently large, unlimited size. We don't need to worry about it. But in reality, and we found, using domain knowledge, we can figure it out. Why? Because the price of individual fund is no secret. It's public information. Assuming we already know which are the 3 funds you are investing, right? then what we can do is we look at their change of price. In the first day, we may have 800 different chart which can be mapped to the same packet size, right? Then we look at the change of price, and we're starting from individual pie chart, and we check and the change of the pie chart according to change of the price. Then we look at the size we observe in the second day. Then we can rule out a lot of possibility. Actually, what we did is, and what we found is, we almost can reduce, the size of anonymity side by 1 order of magnitude. That means the first days there could be more than around 800 different pie chart. But looking at the change of the price, in the second day we can have only 8 pie charts, and the third day only 8. Then within 4 days we can uniquely figure out and your allocation. And such information, such information is publicly available. So that means, if you want to detect this kind of problem, in many cases, you also need to consider domain knowledge, which just makes the whole problem very, very complicated. So just as mentioned, and this has been, and the problem has been caused by some fundamental feature of today's web application. So this is one of the most disturbing, discovery we found. Okay. So such kind of observation, such feature, including significant traffic distinction, just I mentioned, you have a different kind of element. You have a video, you have pictures, and you have JavaScript code, and they all have a different features, and to make things worse, and today's web application, and more or less they use this kind of syndicate technology. That means if they send you a web page, right? The content of a web page comes from a lot of different places. You understand what I'm talking about? And a specific example is the pie chart. Actually, instead of coming from that investment company, actually it comes from Market Watch, another place. So they have this kind of diverse information which we can take advantage of to fingerprint a specific piece of information you entered. So it's very difficult to defend against. Low entropy input. And they just use this Ajax. And the GUI, Ajax widget, right? And and they are increasingly using these kind of things. Just look at Google Instant, right? And they provide all this functionality. Looks like make life easy. Also make hacking easy. And and the stateful communication. Just as I mentioned, the application is stateful, and you can use the state information to piece different kind of resource, different kind of information together to figure out a sensitive data. Your medical record is a good example. I may not be able to uniquely identify your disease, and your medicine and your therapy, but I know they are related because the stateful nature of the application. I piece them together, I can figure it out. Defense is highly non-trivial, and by non-trivial I means and we believe they do not exist an efficient and effective application agnostic approach. And if you know this specific problem, of course you can fix it. But the point is, if you want to come up with a one-size-fits-all solution, it's going to be difficult. So what's the implication of this argument? The implication is, if there do not exist those one-size-fits-all solution, then you have to deal with this problem individually, according to the specific feature of individual application. In other words, when you're developing this type of application, you'd better, just add in a special step to checking, the side channel bug in this application and take step to fix it. Just like you're checking buffer overrun vulnerability and other kind of bugs, right? And our research shows, there exists some straightforward solution, just like padding and and adding noise. But if you pad a package, adding noise and without blindly, without looking into the specific feature application, you may introduce a huge amount of overhead without solving the problem. And here's the example. And we studied, just adding noise. Actually, we studied 2 ways to pad a package. One is called, rounding. One is called rounding. We simply round a package to the size of, just described by the multiple of a specific number. For example, multiple of 1 byte, multiple of 16 bytes, multiple of 32 bytes, so on and so forth. And the second way is called, just random padding. We just simply just pad the original package, just with a pad, and whose length, uniformly distributed between 0 and the data. And we studied these two techniques over all these vulnerable web application. And then we found just if you want to pad pad an online house and this house information system, and what's happened here is you need to prepare to pay an overhead just up to 1/3 of this its communication, the total communication overhead. You have to increase the bandwidth by 1/3 in order to just reduce the risk and to an acceptable level. But for online text, right? Even if you increase the communication overhead by 40%, you still cannot solve the problem completely. And and as I mentioned, there are some asymmetric paths and a lot of asymmetric paths in the application. And so those asymmetric paths they have these features. If you go down one path, they only have one round of communication, for example. And if you go down another path, they have two rounds of communication. And so these things cannot be covered by simple packet size. So you have to add noise, right? So even if you increase overhead, let's see, to 40%, you still cannot completely solve the problem. And of course, in the end, if you pad every packet generated from this application to the same size, then just more or less you can solve the problem. But if you want to do that, the overhead is prohibitive. I forget the number. You can check our paper. I think it's I don't remember. It's 20 times or 200 times. But anyway, it's not something you can accept. Another interesting observation is and sometimes padding could be very difficult in practice. For example, rounding does not seem to be appropriate for the Google Health problem. For the Google search problem. And the reason is whatever come back from Google search engine actually has been compressed. So if Google want to patch the packets to suppress this kind of Wi-Fi sniffing, right? And they have to make a decision when to patch. To patch before the compression or after compression. If they patch before the compression, then after compression happens, packets could still have different size, right? Because compression depends on the content of the packets, right? And just so obvious, this is not a good solution. But if you pad, just after compression, what's going to happen is, just for some organization, and for many organizations, just like, Microsoft, what they are going to do is whenever receive this compressed package, they are going to decompress it. They are going to extract information to check its content. And in the organization, this is something they have to do to make sure everything is secure, right? So when this happens, just obviously, after they decompress packets and send it out through encrypted Wi-Fi channel, right? The packet size appears. Otherwise, you can take advantage of it to figure out your content. So the question becomes, from the Google's viewpoint, you don't know if your customer is going to decompress it or just let the browser to do decompression. You have no idea. So how could you pad it, right? And it's going to be a very difficult problem. And we found random padding does not work well for online investor. Why? And and for those investment company, if you are doing investment, particularly for professional investor, and they may have the tendency to check the same content multiple times a day. Right. So although you have the random padding and this the same piece of information and just hide by the randomness, right? You can do intersection again. The intersection will help you to reduce the effectiveness of randomness. We did experiment and we show this works actually. And there's another caveat here is just I mentioned, and the real web application actually syndicated. For example, and this online investment software, they got the GIF pictures actually from another website. Although that things also has been encrypted using HTTPS, and and they can't patch it itself. What happened is they just embed a tag and into a web page and send the web page to the client. Then client it is client download this figure from the other website. And so that company cannot patch the application. They have to ask MarketWatch and other company to do them a favor to patch the packets on their behalf. So this is going to be problematic. I don't think these things are going to work in practice. Yeah, so just and our conclusion is just just with pervasive of software as a service and all this computing paradigm just the things become life become easier because we are no longer need to buy software. We can just rent the software. It's a very nice thing. But on the other hand, just the development of the software and for the convenience of usage actually expose some many new security vulnerability which adversary can explore. And for this particular problem, side channel problem, we think it's a very serious. It cannot be fixed and just using just application agnostic approach. So the real solution is to just needs to be applied case by case by looking at this specific application and identify just where the problem happens. Then come up with a specific solution to this problem. And in other words, we have to change the way we develop web application to add some additional step to detect side channel information leak and to take steps to fix the problem. So that's the conclusion of our first piece of work. And I'm going to give you guys a very quick discussion of our second piece of work, and which has been just accepted by CCS this year. Just for this piece of work, I'm not going to go to detail. Just I have a very good reason. I have two reasons. And just number one, looks like I only have just 10 minutes left, 9 minutes left. So I don't think I can count all the details. Number two, my students are going to present this work 2 weeks later. I guess some of you guys will go to CCS. So if I present all the work in detail here, and you may not show up in my students' talk. So I just don't want to give my new student an embarrassing investment, and so I still encourage you guys to go to my students' talk if you attend the CCS. It's a very interesting work. So what I'm doing here, just want to give you a 1,000-feet view of what we did. Again, this work has been done by the same team, and the side channel information leaking web application, just I mentioned, is a very serious problem, and the question of how to mitigate this problem, right? Just as I mentioned in the previous slides, to mitigate this problem, the first step and the most important step is we need to detect this problem. We need to detect this problem in a specific piece of code and then locate it, then trying to fix it, right? So detection is the first step. So we need to know how serious the problem. We need to know just where the problem is, and we need to analyze the code to find the problem. And the second step is we need to evaluate it. We need to understand and whether this is such a serious problem, and so that I need to take some action. Why? Because all research show, every single piece of web application actually leak out information, more or less. For example, if you use Gmail, and no calorie traffic feature, I can figure out some of your behavior. For example, whether you're receiving email, whether you're sending email, but you may not care, right? And I'm sending email. So what? As long as you don't know the content of email, I'm happy, right? And but for Google for just and Google search, and you may also put up argument, and my searching words. This is no big issue. But for the health information systems, then just a different story. My health record is something I need to fix it. So the important things here is, once we identify side channel leak, and we need to quantify the amount of information can be leaked out from this channel, so that we can give a developer a kind of feeling, and just whether the problem is so serious and they need to take some action. And so that's the purpose of the paper. We first provide a tool to allow developer to locate the problem. The second step, we let developer to quantify the amount of information leaked from individual program location. And so they can make a decision where to take a further action. So it's very preliminary work, but I think a necessary step. So the idea is very simple, and we use information flow analysis, and just like many other software development tool, and we let the user to mark out the variable which carries sensitive user data. Then we use information flow tracking and to identify the program location where the sensitive data has been sent out to the network. And when this happens, we know this could be an occasion which cause information leak, but we are not sure. So what we're doing here is we instrument this program location, and we rerun the application, do a dynamic analysis, and our purpose of trying to figure out the link between the feature of the traffic and the content of data. And once we establish this relation, and then we can calculate the amount of information being leaked out from this channel, and we use conditional entropy to do the measurement. And the reason we use this kind of mixed static analysis and dynamic analysis is again based upon a special feature of web application. Just the interesting things for web application is even the developer himself has no idea what will be the traffic feature. Why? And today's web application is not something which is running directly on the operating system. They are running over another platform. The platform which is composed of your browser and web server, right? And it is the web server and browser that generated the traffic, and the application itself has no idea about it. So, and we can, and for the developer, of course, they know the source code of their program, but they may not have the source code of the browser, and oftentimes they don't have, they don't have in many cases they just don't have the source code of the web server. So just when we come to that boundary, the only thing that can help us is allow the developer to do this kind of dynamic analysis, and to check if the feature of the package can be linked back to the application itself, and the content of data. And once this relation has been established, and you can just calculate the amount of information has been leaked through this channel. Since I only have 4 minutes, instead of going through all the detailed technique, let me show you another video demo. Make it full screen, and in this demo, and we show how can we use our tool to just analyze application just similar to those text software, right? And so this the testing application we are using, and what we do is so this application is very simple, straightforward. You first input your adjust gross income. Of course, in reality, it's calculated instead of you just not using input. We just want to make it simple, and then you can just connect, you can connect the college credit and different kind of credit deduction. Let's say you enter your gross income. Then you can just claim different credit deduction. Then the system will make a decision according to your income. And to analyze this code, what we are doing here is we can just load the source code into our system. Then the second step, we need to load a user behavior model. And the reason we need this behavior model is because today's web application is event driven. So what happening here is you define a bunch of event, right? And whenever you take a different action, it will trigger different event, and different event will trigger different callback function. So put things together, you have a complicated program, and the user only need to define the different event. And give me different callback function, right? And when you analyze this program, then you encounter a big problem, because the user can have arbitrary behavior, which will trigger different event sequence and give you different program execution sequence, which make the things beyond management. So what we did is, we require the people doing the software testing actually just provide the behavior, the event sequence. So we just look at the event sequence, we can figure out the callback function. We can come up with a whole program and to do the analysis. Yeah. So we have a behavior, we have an event sequence, and then the third step, you have to define the sensitive data. Right? You have to tell our analyzer and which variable actually contains sensitive data. There are a lot of tricky things here, because the different part of program actually they related and in a very subtle way. For example, and just and the obvious things is not this is. For example, the obvious things is just the name of your disease you select you input to the health information system sensitive, right? And this could be the variable, and the variable contain that disease could be something marked out by developer. But even before that, and just some information related to disease has already been leaked out, because just if disease has been entered in a way that just you let someone to first choose the initial letter of the disease, then the server give you a list, then you can choose something on the list. Then even before just and even the name of disease has been formed by the system, just some information related to disease has already been leaked out. So what we need to do is not only do a forward tint analysis to track just and how the information leak out and how the scientific information affect just and a network interaction. We also need to do a backward just tint analysis to find out all the other piece of information related to this piece of sensitive information. So we can find out all the network interaction more or less related to the sensitive data. So it's more tricky than it appears to be. So using our analyzer, we can figure out just and all the condition, including just and control, and including branching condition, just control all the information leak from data flow and the control flow. Yeah. Then in the second step, actually we're doing this kind of rerun test. We instrument the code. And just again. We instrument the code, just and the instrumentation also including this kind of rerun direction, because we want the program and for the right event sequence and to go right to the place information leak will happen. Then we repeatedly test, just the program execution at that spot and using different input value and figure out how much information has been leaked. And so originally, just and we test this specific piece of software, and just at the very beginning, and just and we have attack knows nothing. So just we have a certain kind of entropy value being being kept. Then just and after system repeatedly tested and just and multiple time, and we'll get more information. So the level of entropy has been reduced. It's keep going down. Yeah. Finally, just and after test, and we found just the amount of information has been leaked, just and is significant. We quantify all this information leak and report it to developer, so developer can look at and what type of information has been leaked and the amount of information has been leaked, just to make a decision whether they need to take step to fix it. So instead of going to technical detail, which I don't have time to do, and just I just say what we've done so far is just the tip of the iceberg, is only the first step, a very initial step. Right, and we just did this kind of combination of static analysis, dynamic analysis, trying to figure out the program location where information leak happens, and we're trying to do quantification, right? And the research turned out to be successful, just and we just successfully identify some real and just and some synthesized program information leak from real and synthesized program. But still, just we have no way to guarantee the completeness of our testing. Just it is very difficult. So how to improve the completeness and improve and just at very least give out some measurement how complete the test is, just it could be something non-trivial. And the test model so far is manually generated, and we didn't use automatic method to generate those models. And it could be challenging. and what the tools we developed is for developer. So developer can use this tool to test their own software, right? But think about if you want other party to do this kind of third party black box testing, right? You need a different tool. So that's something we're working on, and we haven't just and as a first step we just detect problem and quantify the problem, right? But we didn't fix the problem. So hopefully in the future just we can come up with a new technique to try to fix this problem. The straightforward solution is, and we can find a nice way to do the placement. If we find some program logic leak out a lot of information, it's highly sensitive, we can place it to either to the client or to the server to reduce the communication, right? And how to figure out this kind of logic placement, but also minimize the communication overhead. And other overhead introduced during the client-server interaction could be a big issue. Okay, that's all my talk. I will be very happy to answer you guys' question. I'm sorry, I know it's already 5 minutes past, but I'm still willing to just if you have any question. Go ahead.
Just a quick question. Mm-hmm. So if someone goes through the trouble of writing software that is impervious to such.
You need to press the mic to hear the questions, please.
So if someone, can you hear me? Okay. So if someone goes through the trouble of writing code that is impervious and resistant to this type of attack, do you have any thoughts on, like, would people actually pay more for it or care, or would companies want that for less liability? I wonder what the implications of something like this, just assuming someone goes through the trouble of writing tax software that costs twice as much maybe or something like that, but gives you really privacy.
Okay, so you are talking about if I give you a perfect privacy protection, right? And just how much cost you are willing to pay.
Yeah. What do you think? Do you think people
Oh, I think this is a very very good question, and frankly speaking, I don't know, just but just I don't know, just and you can see, just if I give you just a better privacy, I'm not going to leak out your salary. Let's see, are you willing to pay me double the price, right? And just and this kind of question, just and I only can give a wild guess, just and for me, I'm not going to do that because my salary is public. Everyone knows. But I bet there is a market, there are a bunch of people who really think that salary is big things. They are going to do that. Just and I think just I think that the television things is turned off, right? The television, the TV broadcast things is turned off, right?
No, I'm still recording.
Oh, you're still recording? Okay.
Yeah.
Just and here's an interesting story. Just and in our paper we give a citation. People did this kind of survey many years ago, and I just ask people, just you have a bunch of privacy things, which one is the most important? And imagine which one is the most important in just under the privacy issues, and surprisingly, and a lot of people point out his salary, their salary is the most sensitive data they want to protect, even above some other things we think is very sensitive. You understand what I'm talking about? I'm not going to say what it is because I'm, you guys still recording. It's going to be something off the record, but whatever. Just I think, just you can. I believe it's just wild guess. Just I'm not an expert. Just and you can find a market.
Experiments with your colleagues in psychology at IU,
Yeah.
with human subjects, and I think that's the only way to find out. Otherwise, it's just speculation, probably.
Yeah, and just and when we talked to Microsoft research team about the possibility, just we develop this technique and to do technical transfer. They're very interested, and looks like industry indeed have this intention to fix this problem. Just and at the very least, you need some way to measure it, to understand it, and some problem may not be a big issue. For example, just a leak out from Google search, right? But if you have a health informatics system, health information system online, and which just leak out, just all the information about, just a patient's health record. And this is going to be something big. You got to take some effort to mitigate it, right? So I think in general, this could be a big issue. And just we need to take some measure to fix it. Other questions?